Hello, I'm Jul Jon General, and I will give an introduction to unconventional quantum circuit simulation as my final oral report for the course CS297 Introduction to Quantum Algorithms. From this course, we learned that quantum computers promise significant speedups in solving problems that are intractable for conventional computers to solve. Of course, there's the famous example of Shor's polynomial time algorithm for prime factoralization in comparison to the most efficient known conventional algorithm, which is in sub-exponential time. But as of 2022, of course, this might change someday in the future. And these are some of the reasons why studying quantum circuit simulation might be important. Number one, constructing a quantum computer is very expensive. For example, Google's Sycamore quantum computers use send control signals to the quantum processing unit using cables that cost $1,000 per 2-foot length. So that's just talking about the cables, not yet the salaries of the researchers, the engineers, the actual facilities for the hardware. So you can just imagine how expensive building an actual quantum computer might be today. Number two, quantum computers are error prone. Quantum systems are require a very sensitive environment. They are very receptive to noise. So any unwanted signal or a change in temperature might collapse the entire quantum system, which is related to number three. There's still a huge difficulty in making bigger quantum computers that are able to solve practical problems or able to execute practical programs, which is related to number two, because introducing more qubits to the quantum system is also introducing more possibilities for error, for noise, which is why as of today most if not all currently existing quantum computers, such as that of Google's, IBM, Microsoft, and other smaller startups, are still in the territory of 100 or so qubits. And since they are error prone, a significant fraction of those 100 qubits are not strictly computational qubits, but qubits used for error handling. So there's still a huge barrier in with the possibility of making a practical quantum computer. But in spite all of those reasons, many computer scientists, of course, still want to study quantum algorithms. It's a relatively smaller field of computer science, and there's a lot of excitement and optimism, and that one day we might be able to construct practical quantum computers that might be able to run our quantum algorithms. Therefore, by finding a way to mimic quantum computers using conventional hardware can help us with the design, the optimization, the verification, and performance evaluation of quantum algorithms. So these reasons might motivate uh, researchers who have no access at all to a real quantum computer. Uh, for me personally, these are enough reason to study quantum simulations, but from another perspective, even if you are already building or constructing a quantum computer, or you already have a small quantum computer, the study of quantum circuit simulations can still help you in these 4 ways. Perhaps there are more, but uh, these are my suggested motivations for those types of researchers who already have quantum computers. So even if you have a quantum computer, a simulation can still help you in designing error correcting codes. That's of course very important with quantum computing. Number two, uh, for example, you have a quantum algorithm. You can run the same algorithm on a real quantum computer and a simulator using conventional computers simultaneously, and you can help that can help you investigate your quantum hardware. So for example, you run the quantum algorithm on those two types of machines, and your expected exponential speed up or exponential improvement in performance is not there. So one hypothesis you can put forward about that is that maybe your quantum computer isn't functioning correctly. Maybe you're running your quantum algorithm on a very expensive conventional computer and not a real quantum computer. Or another hypothesis is that your quantum computer is functioning 100% correct, but the problem is with your algorithm. Perhaps we can classify classes of circuits, which is another way of saying quantum algorithms, where there are no reachable quantum speedups. So maybe your quantum computer is functioning completely well, but you are looking at a problem where a quantum algorithm will not beat a conventional algorithm running on a conventional computer. So those are very important things to consider, things to investigate with a quantum computer and a simulator running simultaneously. And of course, number 4, a simulator can give you additional insight about your quantum computer. A simulator can calculate precise amplitudes of a quantum state, which we know is not observable on a physical quantum computer, because measuring a state collapses the superposition, and you are left with one of the basis states, or ket 0 or ket 1, or if you have more qubits than 1, then ket 0 0, ket 0 1, etc. Okay, so those are two different motivations for two different types of researchers, one with no access to a real quantum computer, and one type of researcher with access to a real quantum computer. So perhaps there's no doubt that for anyone in the field of quantum computing, quantum algorithms, uh, quantum circuit simulation is a field of study worth looking at, or it's a worthwhile uh, research field. There are many ways of classifying simulation techniques, and this is one that I looked at. Uh, this classification is based on if the simulator calculates precise amplitudes, itong number 4. So if it does, it's called a strong simulation, and if it mimics the non-deterministic output of a real quantum computer, then it's called a weak simulation. The majority of literature about quantum circuit simulations focus on strong simulation, which is why today we'll call it the conventional technique. And the weak type of quantum simulation is the unconventional quantum circuit simulation technique. That is the title of this presentation. Since that's what this presentation is all about, or even if that is what the presentation is all about, we still need to describe strong simulation, even maybe even just briefly. And since strong simulations explicitly compute some or all of the amplitudes of the final quantum state produced by a given circuit, it's statistically distinguishable from real quantum computers because those amplitudes aren't observable in a real quantum computer. Okay, so here we have a quantum algorithm, or a quantum circuit, another way of putting it, with 3 input qubits in order to encode 8. So n is 3. It can encode 8 possible input values and 8 possible output values, or we'll call them the basis states ket 00 until ket 111. So in strong simulations, after this entire series of quantum gates at this point of measurement, then we'll have an exponentially large array of amplitudes, meaning if we have 4, then the size of our array of amplitudes will be 2 raised to 4, or 16. So you can just imagine how quickly this array of amplitude will blow up when we increase the amount of qubits in the system. And then from this array of amplitudes, we can easily compute a vector of probabilities by squaring, getting the square norms of each amplitude. So this probability is the square of this amplitude. And then using a random search, a weighted random search on this array of probabilities, then we can simulate a quantum measurement. So in this example, we got ket 011 as the final measurement. As I mentioned before, this part we can never observe in a real quantum computer. Maybe we can look at probabilities or the output sampling, as the papers I've looked at call it. in a real quantum computer. What does that mean? For example, if I run this quantum algorithm on a real quantum computer 8 times, then 3 times out of 8 I'll get 001. 1 times out of 8 I'll get 100. And but maybe roughly 3 over 8 or roughly 1 over 8, because to get almost the exact number, then you have to run the quantum computer a lot more times than 8. Sorry. Excuse me. Yeah. Excuse me. What the papers on quantum simulators show is that although this is quite close to a real quantum computer, it's still significantly statistically distinguishable. This part doesn't, or this whole part doesn't accurately mimic a real quantum computer or the real output sampling on a quantum computer. So that's why we'll look at fast weak simulation, which tries to mimic the non-deterministic output of a real quantum computer in order to produce a sample of outputs that are statistically indistinguishable from a real quantum computer. And since we don't have to return an exponential number of amplitudes after a quantum circuit, then this is better in terms of computer memory. In order to understand fast weak simulations, we look at vector decomposition. Or dividing this vector into subvectors. So if we have a vector of 2 raised to n, then our goal is to also create 2 raised to n number of new vectors of size 1. So that's also one way of saying 2 raised to n complex numbers. How will we go about that? So give it this example of 8, size 8. We'll divide it into two subvectors of equal size. So I get 1, 2, 3, 4 each. So if this indices correspond to the basis states, then we can easily see the subvectors as dividing the original vector in terms of its most significant qubit. So this qubit, this vector contains the elements where the leading qubit, or we'll call it Q2, is 0, here 0, and here where the leading qubit is 1. And then each of these two we can also subdivide with size 2 each, where we can see that is when the second most significant qubit, or Q1 here, is either 0 or 1. So if Q2 is 0 and Q1 is also 0, so these first two, 0 minus 0.612 I, 0.612 I, and then when Q1 is 1, 0, this part, minus 0.612 I. Then we'll repeat for Q2 equals 1. When Q2 is equals 1 and Q1 equals 0, so this part, 354, 0.354. Then lastly, for Q0 equals 0, Q1 equals 1, then we only have size 1 vectors for each, or a complex number. Once we see the decomposition of the original vector, then we can look at the important data structure that fast-weak simulation uses, which is called the decision diagram. We'll just copy this, but we can represent it using a graph. So that's our decision diagram data structure. So we started with the most significant qubit, which is Q2, and then it divides. It can be either 0 or 1, and then it divides again to Q1, which also can be either 0 or 1. Oh, sorry. Zero, 1, 0, 1. And then we get the final qubit, which is Q0, which of course can also be 0 or 1. And then after creating our decision diagram, which is just a graph, the next thing we can do is to put weights at each edge. So one way of giving weights to our edges is to measure their probabilities. So what is the probability that Q2 is 0? So the total square norms of this half where Q2 is 0, which is 0.12 I squared plus C. And of course, this can also be some other complex number, but we just put 0 for convenience. If we take this, then we get roughly 0.75 or 3/4. So that will be the weight here. And then we compute the weight for the right edge here, although instead of computing, we can just subtract this from 1, so we get 1/4. And then for Q1, what do we get? The probability of being 0 and being 1 here, and being 0 and being 1 here. You can see that where 0, 0, 0, 0, 0, 1, or Q1 equals 0 and Q1 equals 1, right, which is 0, 1, 0 and 0, 1, 1. So these two versus these two, we can see that they're equal, so that's easy. You just get 1 here. So in the case of Q2 equals 1, what is Q1 equals 0 here versus here? As we see, they're also equal, so we just get 1/2. Not there. Here you just get also 1/2 here, and then you repeat the process for when Q0 is 0, or get 0, 0, 0, get 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, etc. Then finally, we can rewrite this graph. We can edit the weight on the edges, so that the sum per each row, the sum of the square norms of the edges on each row is equal to 1. So if we have 3/4 plus 1/4, we can just get the root. So we get square root of 3/4 plus 1/2 here, and then on this side we get 1 over square root of 4, 1 over square root of 4, 1 over square root of 4. Yeah. So that's it. We got the decision diagram data structure for the fast week simulation technique. Concluding, by using this method of sampling outputs for quantum simulators, then we can build simulators that are statistically indistinguishable from actually existing quantum computers. And sampling outputs from a decision diagram is slower than the strong simulation technique, but it scales better in terms of memory by kasi iniiwasan yung pag-blow up ng exponentially large array of amplitudes. That's it for my final oral report. I apologize for coughing. I still have some symptoms. I also hope to look at more, two more simulation techniques for this oral report, but after my isolation, I didn't have the time. But I still hope to go into more simulation techniques with my written report. That's it for now. Thank you very much for the semester, everyone, especially Dr. Adorna. Again, thank you and goodbye.